Question 1. In the sequence 7, 76, 769, 7692, 76923, 769230, and so on, the nth term is given by the first n digits after the decimal point in the expansion of 10 over 13, and that's 0.769230, and so on. Prove that of the first 60 terms of the sequence, at least 49 have 3 or more prime factors. Repeated prime factors are allowed. For example, 76 is 2 times 2 times 19, and so has 3 prime factors.
So this problem concerns a sequence of integers which are derived from the decimal expansion of the fraction 10/13. So it seems sensible to begin by actually doing that division, doing the calculation to find the decimal expansion of 10 over 13 in the hope that'll help us to understand this sequence of integers a little better. Okay, so I'm going to divide 10 by 13. I've set it up so that my answer will appear underneath the 10, leaving a little more space for the remainders above, and it might be useful to have the 13 times table on a piece of scrap paper. 13s into 10 goes 0, remainder 10. 13s into 100, 7, remainder 9. 13s into 90, I think, goes 6, remainder 12. 13s into 120 is 9, remainder 3. 13s into 30 is 2, remainder 4. Into 40 is 3, remainder 1. And 13s into 10 goes 0, remainder 10. But this is a situation we saw before at the beginning of the calculation. So from this point on, the decimal expansion of 10/13 will recur. So this is going to be a recurring decimal, and it's going to recur with period 6, and we're going to use that to look at our sequence of integers. So here we see the sequence of integers given in this question arranged in a table with 6 different columns, A, B, C, D, E, and F. As we go down each row in this table, we add on the string of digits 769230 on to the previous number at the front. To save space, I've indicated that using a little tilde. So this tilde here is 769230 and then 76. 2 tildes means we stick that on twice. We're asked to show that there are 49 of the first 60 numbers in this sequence that have 3 prime factors, where we can count the same prime factor more than once if we need to. So we need to imagine our table here having 10 rows in total. Let's have a look at column F. We see here a number that ends with a 0. That means it's divisible by 10. Every number in that column is going to be divisible by 10, and so each one of them can be written as 2 times 5 times some other number f. We should check, of course, that the number f is clearly bigger than 1 for any entry in that column, and so has a prime factor, so every entry in column F has got at least 3 factors, prime factors. Okay, let's look at another column. B looks hopeful. The top number in B is 76, that's divisible by 4. And in fact, to check if an integer is divisible by 4, we only need to look at its last 2 digits. That's because the difference between an integer and its last 2 digits is always a multiple of 100, and therefore a multiple of 4. That means that every entry in column B can be written as 2 times 2 times b for some integer b. And again, clearly that integer b is bigger than 1, so has a prime factor. So every entry in column B has got the 3 prime factors we're looking for. Exactly the same thing applies to column D. 92 is divisible by 4, so every entry in that column will be. So much for divisibility by 4. The next fruitful column to look at is actually column E. If we look at that, it's not an even number at the top, so the next thing to try is it divisible by 3? So of course we add the digits. 7 plus 6 plus 9 plus 2 plus 3 is 27. So delightfully, it's not only divisible by 3, it's divisible by 9 because its digit sum is. Even more delightfully, as we move down column E, each time we go down, we add the string of digits 7, 6, 9, 2, 3, 0 to the front of the previous number, which adds another 27 to the digit sum. But that means the digit sums are all multiples of 9, and so every number in column E is a multiple of 9. That is 3 times 3 times some integer e, which is clearly bigger than 1, and so contributes another prime. So far, so good. The remaining two columns are both headed by prime numbers. 7, 6, 9 turns out to be a prime. But that's okay. The question is asking us for 49 numbers with 3 prime factors. Remembering that our table's got 10 rows, we've got 40 accounted for so far, so we're just looking for another 9. It's not immediately clear which column we should focus on now, whether it's A or C. We'll try A first and be delighted when that turns out to be a good decision. This number here, 7692307, it's not divisible by 2 or 3 or 5, but a quick check on some scrap paper shows that it is divisible by 7. In fact, it shows that 76923 is divisible by 7. And as we move down this column, what we're doing is adding 76923 times a power of 10 to the previous number at each stage. So we're always adding another multiple of 7. So that little calculation shows that every number in column A is a multiple of 7. Let's write that here as 7 times A. We're very nearly there, but unfortunately, it's not yet clear that these numbers all have 3 prime factors. We know they're 7 times something, but there's just a disturbing possibility that perhaps some of those numbers A might themselves be prime. So to finish the problem, we're going to need one more new idea. So we're looking at column A of our table, and we know that every entry in there is a multiple of 7. We'd like to show that every entry, apart from the top 7, is divisible by 3 primes, so we'd like to show that none of them are of the form 7 times a prime number. It would be great if we could find some small prime, like maybe 11 or 13, which divides all of those numbers, then we'd be finished. But unfortunately, that's impossible because no such small prime exists. To make more progress, we need to look again at where these numbers actually came from. So the original 7, we got that when we were dividing 10 by 13. We had that 13 into 100 goes 7, remainder 9. 100 is 9 more than 13 times 7, or put another way, 7 is 100 minus 9 over 13. In the same way, if we continue the division, we learn about the number 7, 6, 9, 2, 3, 0, 7 is, I think we're going to need 8 zeros. And on the top there, we might recognise a difference of 2 squares. So that's equal to 1/13 of 10,000 minus 3 times 10,000 plus 3. Now, both of those factors in the brackets are considerably bigger than 7 times 13. So when we divide out the 13, it definitely can't be the case that this prime factorization becomes 7 times a prime number. And that shows, without actually explicitly factorizing it, finding the prime factors, that this number here has got at least 3 different prime factors. The general case is exactly the same. If we go down anywhere in this column, we're going to find a number of the form 10 to the 6k plus 2 minus 9 over 13. That's equal to 1/13 of 10 to the 3k plus 1 minus 3 times 10 to the 3k plus 1 plus 3. Again, both of those are considerably bigger than 91, so when we divide out the 13 to get a product of two integers, it can't be the case that it's 7 times a prime. So apart from the original 7, every number in column A has got 3 prime factors. Add those 9 new numbers to the 40 numbers we got from the other columns in the table, and we find precisely the 49 numbers needed to solve the problem.